Hi, my name is Bill Kinney and I'm a math professor at Bethel University, and this is a second video that I'm making in a series on doing arc length calculations for parametric curves. Again, I'll emphasize, as I did in the last video, that I'm not explaining this formula right here. I'm just showing you how to use it because these integrals end up being kind of tricky. So what's our problem this time? Our problem is to take this particular parametric curve. C of t is a point moving around in the plane whose x and y coordinates depend on time. X equals 3t and y equals 4 times t to the 3/2 power. Assuming we start at time 0, there are two things to do here. A, find the arc length of the path for the interval 0 to 2, get rid of that extra 4 there. And B, find what I call the distance traveled function, how far the object has traveled from time 0 to time t, assuming that this is modeling the path of an object that's moving. And that is really what the main point of parametric curves is in a lot of situations. So we want to do the arc length calculation here. So we'll apply the formula here. There it is. And now just plug in our functions. Again, x of t is 3t, so x prime of t is going to be 3. Y of t is 4 times t to the 3/2 power. Differentiate that, you're going to bring down the 3/2. The 4 will cancel with a 2 to leave ultimately here a 3 times 2 is 6. And we'll have t to the 1/2 power. 6t to the 1/2 power is the derivative of that. And the interval here in part A is from 0 to 2. So the limits of the integral are going to be from 0 to 2. So now it's a matter of simplifying this a bit and seeing if we can figure out what to do with it. That's 9. This is going to become 36t. There's no problem taking the square root of t in here because t is a non-negative number. So this is the integral that we're going to do. I would encourage you to go ahead and try it on your own. Pause the video and come back. If you have come back now, or if you haven't paused the video, we'll go ahead and do it. The best way to do this kind of integral is with a substitution. It looks a little complicated because of the square root, but the 9 plus 36t in there is not too bad. We can do a substitution. Let u equal 9 plus 36t, so that du will equal 36 dt. As far as, and I'm gonna go ahead. I'm not gonna find the antiderivative first, and then plug in the limits of integration next. After that point, I'm just gonna change this definite integral into another definite integral involving u, and I'm never going to go back to t again. So I have to change the limits of integration. Note that when zero is the lower limit of integration, so when t is 0, what is u? I've got to use this equation to figure out that the lower limit in terms of u is going to be 9. So this will be a 9 here. If I can highlight it. And then when t is 2, plug in t equals 2 here, you're going to get 36 times 2 is 72, plus 9 is 81. This upper limit of integration in terms of u is going to be 81. The inside of the square root is u, so we really have a square root of u here, or a u to the 1/2 if you prefer. And dt is going to be 1/36 du, because du is 36 dt. So I'm going to get a 1/36 here. 1/36 du. And now I can just do this definite integral as it stands. I need to take the 1/2 and add 1 to it to get 3/2. And that 3/2 is also going to be on the bottom like this. If I'm going too fast for you, probably want to pause it and think about it. All right, let's see, 36 times 3/2 That's going to be, what, 54? Double check that. Yes, 54. So it's going to be 1/54 here. U to the 3/2. I plug in 81, so I get 81 to the 3/2 minus 9 to the 3/2. This can be simplified. I picked the numbers to work out nicely. When you raise a number to the 3/2 power, first you need to take the square root. That's like raising to the 1/2 power, and then cube that. So with 81 to the 3/2, we take the square root of that and get 9, and then we do 9 cubed, and that's 729. Check that down here with Mathematica. So we're going to have 729. 9 to the 3/2, the square root of 9 is 3. 3 cubed is 27, so I'm going to get a 27 here, all divided by 54. And then 729 to minus 27 is 702 over 54, and this fraction can be reduced. 702 divided by 54 looks like it reduces to 13. Nice. So the arc length here is 13. That'll be our answer for part A. See if that seems reasonable. Here's the curve. Yeah, that looks reasonable. That looks like it might be about 13 units long. And in fact, if I've done everything right, it should be. We can also check with Mathematica on the integral itself. Let's go to the original integral. Yes, it's 13. Okay, that's part A. Let's see, I have about 4 minutes if I'm going for a 10-minute video here. I'll try to see if we can get part B in quick. So now, what's the difference here? We're trying to find the distance traveled function, which is really, you might call it the arc length function as well, but I like to think of it as distance traveled for an object, starting at time 0 still. So A is still 0, but I want to find this as a function of t. I want the ending value of t to be a variable. And in fact, I'm going to go ahead and use a t here as the ending value of t. If I do that, well, some people get sloppy and continue using a t inside the integral for the integrand, but I'm going to use a different letter. I might as well use a tau, since tau is the Greek version of t. And so this is the integral that I need to do to get the arc length, the distance traveled function, a function that's going to tell you how far you've gone in a given amount of time. As before, I'm going to do a substitution. Same substitution as before. U is going to be 9 plus 36. Well, okay, this has got to be a tau here. And this will be a d tau here. Let's see. So what's going to change here? Quickly make the changes. By the way, I think it is good to take notes on this stuff. Maybe I should have told you that before. You might want to pause the video and take notes and think about it and then come back. Anyway, this is still going to stay a 9. This 81 is going to become a 9 plus 36t. I'm plugging t into this equation over here in place of the tau to get that upper limit. So that is supposed to be a t here. This remains still u to the 1/2. Really, compared to last time, the only thing that changes now is this 9 plus 36t is in place of the 81. And maybe we want to just leave it like that. Probably could be simplified more. For example, we could take a 9 out of both terms here, factor it out to write this as 9 times the quantity 1 plus 4t, and 9 to the 3/2 is 27. Maybe I'll go ahead and do that just to show you here quick. I could really have another 27 out here and a 1 plus 4t in there. And then I could also factor out the 27 and divide by the 54 and ultimately get a simplified answer with a 2 down the bottom. 27 in both spots is going to cancel because I can factor it out. So that looks like about as simple as it can go. This is a function that's going to tell you how far the object has gone if it starts at time 0 and goes up through time t. Okay, let's check it. So this is again going to be t here, and I'll go ahead and make this a tau here. Okay, well, it's got this conditional expression here because Mathematica is wondering what I'm assuming about the value of tau. But you can see this is essentially the same formula here. All right, so that's the end of this video.